Welcome to the video where I want to summarize everything we covered in Calculus 1 class. Plus minus a topic depends on the book, depends on the school. But it will be nice to cover what did we do for 4 months and to have a big picture of where we're going after this and why all of this is important. So as you remember, first we started with limits. We introduced the idea of the limit as approaching something, sometimes from the left, from the right, or even far and far to the infinity. And we taught you left limits, right limits, two-sided limits, and this gave us the idea of what does it mean to be continuous, not to have any gaps, any jumps, and any asymptotes. And we were asking, how do you know if the function is continuous or not? And that's going to be very crucial in your career because you will be shocked that most of the functions are actually not continuous and you'll have to learn how to work with them. We taught you how to calculate limits in complicated cases, infinite cases, or just a simple one when you need to work with a square of sum or square of differences, and so on. This squeeze theorem was introduced, and I always introduce it calling different names. Americans like to call it sandwich theorem because you guys like sandwiches. And in Russian-Ukrainian culture, we actually sometimes calling it as a policeman and two policemen and a drunken guy theorem. The drunken guy goes in the middle, and then the two policemen taking the drunken guy from sides to the police station. Infinite limits and limits at infinity introduced to us vertical asymptotes and horizontal asymptotes, VA and HA. Vertical asymptotes are the one that usually makes denominator 0, so that's where some kind of DNA things is happening when x is approaching just, typical number a. And f of x is jumping to infinity or minus infinity, up or down. Horizontal asymptote is the one when x is going to really far to the right or really far to the left, but the output is a finite number. And that gives the idea that the function really far to the right or to the left stucks around some kind of number and gives you the horizontal asymptote. Then we definitely made sure that you guys understand what does it mean to be continuous and discontinuous, and we taught you types of discontinuities like a hole. That's the only one you can fix, and we call it removable discontinuity, a vertical asymptote, and a jump. And we were asking you to figure this out and to fix discontinuity if it's possible, or to identify where we're working with asymptotes. And that was a chapter about limits. From limits, we introduced the idea of derivative. As you remember, we were asking you to find derivative using the definition. And by the definition, it was kind of long process using the limiting position of the secant line. The secant line over here is the ratio of the change of the outputs over the change of the inputs. Basically, change in y over change in x. But if we want to keep moving the secant line the way that it will touch the function only at one point, then it becomes a tangent line. So the tangent line is literally a limiting position of the secant line. And that's why the limit was handy here and help us to define the idea of the derivative through the limit. And we were asking you to create the equation of a tangent line and so on. The idea of the derivative was introduced as row change in output over row change in input. Then we wanted to make it perfect, so we introduced limit and we made sure that the change in input shrinks to 0. So that it's that moment, micro moment we are looking at. It's so small that we could call it instantaneous change. And then when the limit was introduced and change in input was shrinking to 0, the whole result gave us tangent line or derivative, instantaneous rate of change. And then as you can see on the left, we had tons of stuff here to go through. Derivative as a function, basic rules of derivatives, that's the one you guys liked a lot, because basically we told you the power rule and those are simple ones. And we also introduced higher order derivatives, f prime, f prime prime, f prime prime prime. Then it switches to the numbers, fourth derivative, fifth derivative, and so on. Product rule and quotient rule. Those at the beginning looked complicated, but now you know that actually these are the most straightforward formulas, because after that we went to chain rule. We also introduced derivatives of trigonometric functions. Sine gives you cosine, cosine gives you minus sine, tangent and secant, cosecant, cotangent. Then chain rule started, and that's the one I usually introduce using Russian dolls, which basically means that we have nesting, like a nest, nesting of functions. Function inside of the function. Makes sense? And sometimes people teach it using onions. When you work with chain rule, you basically unfolding onion layer by layer. And now you know what's the challenge there. The challenge there is to keep the previous function, differentiate it, but keep the function inside the same, then times the derivative of the function inside, then times the derivative of the function inside, then times the derivative of the function inside, and until you're done. Implicit differentiation explained to us how to differentiate functions if we don't have explicit writing for the y. So for the function, what if we don't have y equals 5x squared? Then find y prime. That's simple. But what if y is hidden somewhere? And what if it's scattered everywhere? And what if you cannot even solve for y? Then implicit differentiation was introduced, which basically says, stay calm and just differentiate everything you see, but keep in mind which function is independent and which function is dependent. And I gave you guys steps, and the steps work up until you hit Calculus 3 class, where implicit differentiation will be done in 3D with 3, 4, 5 dimensions and many, many variables. Then we introduced you guys exponential functions, how to differentiate. Before exponential functions, we introduced related rates. Remember, they followed implicit differentiation right away. And related rates finally introduced some kind of applicational problems. And basically we had some kind of changes, and they were related by some kind of third rate. For example, the tree was growing up, but the trunk was growing left and right. So the thickness of the trunk is growing horizontally, but the tree is growing vertically. Height of the tree is related with the thickness of the trunk with respect to the third rate t. And so on and so on. Same with the ideas of the balloon being inhaled, and the volume of the balloon was increasing, the radius was increasing, and these guys were related with respect to time t. So there was a third rate. In Calculus 3, we're going to introduce much more interesting ideas of multivariable calculus, when you will have 3 variables, 4 variables, 5 variables, and they all have different connections. Inverse functions is not the most favorite part of the learning Calculus 1 class. Basically, we ask you to undo whatever was done. That's a pretty cool idea. That's you actually want to know what happened to sine of x if I know that it gave me pi over 2, and square root of 3. So what kind of input gave me this output, and when I actually can even find that exact one solution for the input if I know the output. And we told you that it's possible to do if you can pass the horizontal line test. And parabola doesn't pass horizontal line test, sine, cosine do not pass, but somehow we know that there is arc cosine, arc sine, and somehow we know that the square root undoing quadratic functions. So we also introduced the idea of the restricting the domain method, and then ask you to find inverse functions. That's a very practical idea, because in many applicational problems we know the result, but we don't know what gave us this result. Like we see the tornado, but we don't know when it started, or we know the earthquake is happening right now, but it would be very good for people and cities to know what caused the earthquake. So in the future, we can predict it and tell people to hide days ahead of time, not just minutes. So some of these inverse problems actually worth Nobel Prizes if you can figure out what caused cancer mutation cells or tumor cells. Then you can predict in the future when it's going to happen, and you can get Nobel Prize for that. Logarithmic and exponential functions and equations were introduced. This is one of my favorite topics. I like logarithmic functions. At the end I will tell you why. And we told you properties of logs and exponential functions. How do they behave, how the graph looks like, and also that they are inverse to each other. A to the x undoes log base ax and vice versa. Derivative of logs. That was a very fun topic because e to the x gives you e to the x, unless it's a to the x. Then you need to multiply by the log of the base. Log gives you, derivative of log gives you 1 over x. Unless it's log base a, then you also divide by log of the base. That's a pretty cool idea, and we practiced like crazy taking derivative of logarithmic exponential functions. You will see that most of the applications you'll be working in your major will have exponential functions there. And since there are exponential functions there, logarithmic functions will be there as well. Logarithmic and exponential functions in the equations. And then also introduce logarithmic differentiation. Logarithmic differentiation basically means we're doing implicit differentiation, but with extra step at the end, because at the end we do know what y function used to be, so we can plug it in. And the idea is to avoid working with examples like this. F of x is a huge fraction with exponents and so on. Instead, I'm applying log on the both sides, simplify it as much as I can using properties of logs until I get this nice written form. Then I can differentiate this form instead, and derivative of that form is much easier. And then, since you put log on the both sides, you will have to undo it, and that's why at the end we need to, we put log on the both sides, and when we're differentiating it, f prime pops out, and we need to isolate it. To isolate it, 1 over f should be multiplied by both sides. Then, we also introduced inverse trig functions, which is arccosine, arcsine, arctangent, arccotangent, which is a pretty cool idea. But also we need to remember that they all have different domain and range, and those can be found from the original function. And also remember how we build them. We draw y equals x function and use it as a mirror to mirror the original function. And that's how you build inverse functions. So here we just found arcsine, arccosine, arctangent, and so on, and gave you formulas for the derivative of all of these. And so you will see that this will be top 1 topic in Calculus 2 class. At the beginning of it, we will be working with these functions like crazy. That was kind of the end of the chapter of Introduction to Derivatives. And then we start doing applications of derivatives. And this is a long list over here. What can you actually apply the derivative to? And of course, it's not full. This list is huge, and that's what we could fit in Calculus 1 class. So each school decides what to put in applications of the derivatives. But most of them definitely agree that linear approximation and differentials should be introduced. That's actually a topic that showed up only a decade, I think, ago, because computers became popular. And since this is basically the idea of approximation, and I showed how this approximation was shown in the Hidden Figures movie, and it was true, that's what they used, linear approximation there. And that's important to teach, because many of you will be computer scientists or engineers, and you'll be actually doing that in your computers. Biologists and statisticians doing that as well, and they've been paid for that really well. L'Hopital's rule usually is the favorite topic, right? It was so nice. Basically, you just work with limits again, but now you can use derivatives if it's 0 over 0, infinity over infinity case. Just differentiate each function and work with the rates instead of the original functions. That was the idea of the L'Hopital rule, and we practiced it like crazy. And here's the idea. two functions and we want to find the ratio, the limit of the ratio of those functions. Instead, when you zoom in those continuous nice functions, they are looking like lines anyways. So that's why we can justify that. You can use linear approximations of those functions, and those are exactly derivatives basically. Basically, derivative approximates the curve function. Then we learned what happens with the limit at infinities. Maybe that topic was a little bit in different time, but I remember I introduced it here. What happens with the limits at infinity minus infinity, and how do we work with these? And also I like introducing the different speeds of different functions. The slowest one is a constant. Then log is faster than constant but slower than linear function. Then polynomials happen. Then exponential function is really fast. Factorial function, that's n factorial, is faster than exponential. And n to the n is even faster than that. That helped us to work with intermediate forms chapters when we had three cases. And most of the time we just used L'Hopital rule by moving the case into infinity over infinity or 0 into 0 case. So we learned 0 over 0 case, infinity over infinity case, and we use L'Hopital rule for that. When we had 0 times infinity, we just were writing it as the fraction and using L'Hopital rule. Infinity minus infinity, we were trying to simplify somehow, factor out, maybe using properties of the log or trigonometric function identities. And then three cases, 0 to the 0, infinity to the 0, and 1 to the infinity. All of those cases have different steps to work with, and also I justified in my classes why these cases even matter. And here is the summary. You use L'Hopital rule for three first cases, and the last three cases, since we're raising something to something and we don't like that, this is where we apply e to the ln idea. Since I don't like having something raised to something, I'm applying logarithmic function to both sides. Logarithmic function to this limit. Then whatever was an exponent goes down. I'm working with that function instead, usually going back to the L'Hopital rule, and then to undo whatever I did, I apply e to the whole result. That's what we did. Now, then finally we start applications of maximum and minimum. That's my favorite topic, because this is where we're introducing critical points, finding maximum, minimums, increasing, decreasing. I love it. I introduced it using COVID-19 graphs, which were real graphs created from the data of how many people got sick and how many total sick people we had. And as you can see, the number of sick people was increasing on the left and it was increasing on the right. And it means there should be a maximum somewhere. So we're teaching you how to find global maximum first. And we told you that global maximum exists if we're working with a continuous function on the closed interval. And then we told you how to find local minimum. And we told you that you can use first derivative test, second derivative test to find these local minimums, global minimums, and so on. Increasing first, then decreasing, that's maximum. Decreasing first, then increasing, that's minimum. Second derivative test introduced concavity, and also still could tell you something about local maximum, local minimum, using this funny memorization hint. If second derivative is positive, the original function is smiling, so we have a minimum here at the tongue. If second derivative is negative, we have a grumpy or frowny face, then we have a maximum here where the nose is. Now, I also mentioned which graphs we expect you to know. That's because students asked me to point out which graphs we think you're supposed to know without a graphing calculator. So I listed them all here. And then we start graphing functions after this, because we learned everything. Well, everything, not everything, but at least we learned and could follow this list. In this list, we tell you, okay, now you can graph the function without a graphing calculator, and this is amazing. We know that first you identify a domain, then find y and x intercepts, Then check if the function is symmetric, has any symmetry. Then find if it's periodic, like sine or cosine. Then the calculus starts. Find vertical, horizontal asymptotes, I just mentioned them before. Then use first or second derivative to identify local minimum and local maximum, where the function is increasing or decreasing. Then, using second derivative, identify where the function is concave up, concave down. Does it have points of inflections? And finally, you can graph the function. And we are giving you different graphs of the functions, and look how beautiful all the work looks like. And at the end, you can create something like this without a calculator, which is really amazing. And you can be proud of yourself, because this is hard work and actually accumulates all type of knowledge. Limits, differentiation, first derivative, second derivative, analysis, everything. We're going to do this again in Calculus 3 class, but in higher dimensions, and you will be amazed how beautiful it is. Now, I compared graphs and properties between first derivative, second derivative, and third derivative. What do they mean? So we can expect you to know what it means to have a positive second derivative and so on, or negative. And then optimization problem started. Remember the objective function, constraints, all of that. You need to read carefully the problem and then identify what is the objective function and what do we want to do with it, to maximize or to minimize. Then we want to have constraints in this case. In Calculus 3 class, we're going to teach you how to work with multivariable problems when you have 3, 4 variables and so on. In Calculus 1 class, we were using constraints to solve for one of the variables, plug it into objective function. Then the objective function becomes one variable function, differentiate it to find maximum minimum, justify that it is global maximum minimum, answer the question. And then I mentioned many applications. For example, in the nature, we have optimal shapes already done, like the eyeball is basically an almost perfect sphere, or why windows are mostly squares, or even the idea that you can literally optimize how do you go to work or to school. Or the ladybug is almost perfectly hemisphere, or why the shapes of different leaves have these types of shapes, and it really depends on where the tree is growing. In the windy surroundings, it will have different shape of the leaf versus on the peaceful forest. And this helps trees not to break because of the aerodynamics. And this is the example of the shape of the tree spinning, not to break. Those trees grow on the edge of the canyons. You can go to the Grand Canyon and see it there. And that's the basic aerodynamics from physics. You will learn it if you take physics classes. And that's all basically using optimization problems, first derivative, second derivative, and so on. So now you know how people build stuff and how nature created this stuff. We also did problems on minimizing the cost function, building the fence with the minimum cost. There's a lot of applications to this. In business classes, we teach how to minimize the cost of the business problem if you want to sell some items on the online website and so on. How to maximize the profit and revenue. There was an open box problem, if you remember. Those are very classical problems, and we tell you that all of those things are not random. Those boxes you receive from FedEx are having those shapes. That's not random. It was actually optimized for the customers to be able to fit as many items as possible. When we finally finished working with optimization problems, we hit the last chapter. For now, we call it antiderivatives. And basically, it was one of the applications of derivatives, which is undoing the derivatives. What if you know the speed, but you want to know the distance? So to find a distance, you need to undo differentiation of the speed, right? And so on. And that's what we call antiderivatives. But now you know it's actually indefinite integral. And we just ask you with common sense, what is the antiderivative of 3x squared? What gave you 3x squared when you differentiated it? Oh, that was x cubed. But also x cubed plus 5 and minus 3 and so on. So plus c showed up as an arbitrary constant. And it created the family of the functions. Apparently, when you undo differentiation, the answer is not unique. And that's why the plus c makes a family of functions, which basically shifted up and down by c. So that's where differential equations happened. Differential equations or initial value problem, they have some kind of data given. For example, you want to find position from the velocity or even from acceleration. That means you're integrating the acceleration twice or velocity once. But how do you know the exact answer if the answer always gives you the family of functions? Well, we give you some kind of data. The speedometer recorded that at some point of time the speed was that, or the distance was this, and so on. And that's how from the whole family of functions you can pick the one that matters for you based on the recorded data, based on the initial value. And that's why it's called IVP, initial value problem. And it's also called differential equations because differential equations are equations that have derivatives in it. Finally, integration started, if you remember, with areas under curves. And we ask you, do you know what's the idea of the integral? So the derivative was slope of tangent line, instantaneous rate of change, and so on. But undoing all of this actually has so many applications, and your goal is to know it's not just about the area below the graph. The main idea was accumulating something which changes all the time. If you accumulate the constant change, that's fine. So velocity is a change, right? It's speed, how much the distance changes, how fast the distance changes. That's velocity. But if the velocity or the speed is the same, 60 miles per hour, that's constant speed. That's basically what happens if you hit cruise control and fix it with 60 miles per hour. Then you know that you need to multiply velocity by the time, and let's give you the answer. How far did you go? 60 miles per hour for 2 hours. Okay, I traveled for 120 miles. But how would you do this multiplication if the change is changing as well? So first speed was small, then faster, then faster, then slower, then slower, then slower, then slower, then faster. How would you perform a product of something which is changing? And that's why I was introducing it this way. 2 times 2 times 2 times 2 times 2, that's 2 to the some power. That's how exponential functions were created, right? And that speeds up the product when the factors of the product are the same. But what if they're not the same? What if it's 2 times 3 times 7 times -5 times 2.3? What the shortcut is going to be for that? Integration will be a shortcut for that. And then we introduced to you areas below the graphs. This is how they look like. This is real data, again, from the COVID-19 data on the patient situation. And as you can see, you literally write down how many people got sick. And then you connect those bars through the graph. And that's how the idea of the area below the graph shows up. What will this area tell me? The area below the graph, which was created from the data of the remaining confirmed cases daily, will give me total number of people sick from the first day to the last day. So this is the idea, 2 different areas for 2 different scenarios. If we do isolation versus if we don't do isolation, different situations. And then we explain that you can approximate the area in different ways. First of all, we taught you that using rectangles is kind of a smart idea because we know the area of the rectangle. We know that. And it makes sense to use what we know. That's what human beings like doing. We know how to use rectangles, then let's use rectangles. A times B, simple as that. But actually you should know that in some problems people use triangles to fill in the area, which is pretty cool. And that actually makes sense for spherical objects and so on. Some people use parabolas. We will teach you that in calculus 2 and 3 classes. Why not to use parabolas to approximate something that has curves? And even trapezoids. That will be called trapezoid rule. And you will learn that in calculus 2 class. For now, we taught you only rectangles. And the more rectangles, the better. But also, you kind of need to agree how the rectangle will touch the graph of the function with left endpoint, right endpoint, or midpoint. And that's where all those problems showed up. The more rectangles, the better, so the limit will happen later. And we will tell you that if you actually use the limit and make sure that we have infinitely many rectangles, then it doesn't give you the approximation anymore, it gives you the exact answer. And that's where the Riemann sums show up. If you have this limit, the size of each rectangle becomes so small that it's basically a straight line. And then with all those small rectangles, I can exactly fill in all the areas. Make sense? But how to do that? How to make such a thin rectangles? If delta x is the base of each rectangle, then I want delta x to go to 0. That's where the limit shows up. The base should be super small, or the number of rectangles should be super big. The limits as n goes to infinity, that's how many rectangles I have, of the sum of areas of all of those rectangles, where the base is delta x the same, but the height is the output of the function at that location, then it gives you exact net area. Net area, not approximation anymore, but exact result, using Riemann sums and this sum sigma notation. Here it is. So the notation looks scary, but you can now show it to your parents and proudly say that you understand this. You're becoming basically a scientist by understanding this international notation, and this is well known around the world. Then we told you that actually this is going to be called definite integral from a to b, and the connection was upper limit of integration, lower integral limit versus limit and the sigma notation. And then we taught you how to find all of these. That's the variable instead of the integral is actually a dummy variable, and so on. How to actually find and calculate the definite integrals. First, we taught you how to use geometry. For example, if you have a trapezoid or triangles, we know areas of these. That took time, but it worked. We also taught you properties of integrals, that if you put a negative sign in front of it, you can change the limits of integration. Integral from a to a is 0, and so on. Integral of sum or difference is sum of difference of the integrals. The constant can be taken out, and also you can break the area or the integral anywhere in between, and then you will have two integrals versus one. Also, we taught you something about the symmetry, and we gave you examples where the symmetry was convenient to use. Finally, displacements versus distance topic was kind of confusing, and I will go into this topic in a second, because first we introduced you fundamental theorem of calculus, second part. That's the one when we taught you. Just find the antiderivative of the function inside of the integral and plug the upper limit of integration, plug the lower limit of integration, and find a difference. F of b minus f of a. That was a genius idea, that something so complicated became so simple, and usually the simplest ideas are the most genius ones, and this is the one. This is the elegant solution of how to find how to find definite integrals exactly and fast. So we taught you different examples, and we practiced a lot how to integrate x squared from -1 to 3. Well, that's x cubed over 3, and then plug 3 and plug -1, and you get the exact solution, exact area, exact answer for the definite integral. That was fundamental theorem part 2, because the second part actually teaches you how to differentiate the definite integral, how to differentiate. And then we find out that if we want to differentiate definite integral, that's basically undoing differentiation. So we just take this x and plug it in, and there was a whole justification why we're doing that. And then I introduced 3 cases. The simple one, when you just plug in. When you have to flip x, integral from x to b can be changed to integral from b to x if you put negative sign in front of it. When there's a chain rule involved, so now it's not still x, it's still x cubed. Still plug it in, but then multiply by the derivative of the function, 3x squared. When you have integral from the function to a function, then just break it. And then it will be integral from a function to a number, and then from the number to a function. And that's it, 3 cases. Distance and displacement showed you that those are not the same thing, just like speed and velocity are not the same thing. So position is position. Position of the object is the location of it, right? Velocity, though, can be positive or negative. That's an interesting idea because the speed can be positive or negative. Displacement. What do we want to think about? How far I am. So if I want to talk about displacement, then it's going to be exactly the integral from a to b. But distance traveled, that will be absolute value of the function inside of the integral from a to b. So if I want to know how much I traveled left and right, left and right, left and right from this chair. So I was walking away from this chair. I was walking to the right, a little bit to the left, and then left over here. To know how much I walked, I will have to find distance traveled. So I need to use absolute value to add all of those changes, left, right, ignoring that some of them are positive and some of them are negative changes. Then it will give me how much I walked. Basically, that's what your device, either it's a watch or a phone, tells you if you have counting app that counts how many steps you do. But if you want to know displacement, that's basically answers the question, where am I away from the chair? I am moved from here to here, done. So displacement will give me how much I displaced myself away from the chair, the final answer, regardless how many times I had to come back. Then I use just the integral. And that was the big difference. So I ask you to find both. The first one, the displacement is easy to find, but the distance you have to actually apply absolute value, and we explain step by step how to do that. Finally, we introduced absolute value function. That basically asks you, if we know the area below the graph, or basically the definite integral, do we know the average? The average area. So if the area below the graph shows me how many total patients I have from day 1 to day 9, do I know what was the average number of patients per day, right? At some point I had a lot, 12,000 patients, but at some point I had barely 9,000 patients, or at some point I even had 6,000 patients. So what was the average? The average number of patients per day is 10,000 over here. How to find it? That's what you call average function, which basically take the integral from a to b, and then don't forget to divide by the length of the interval you are integrating on. So I'm dividing by b minus a. And that's what we did. We gave you examples how to find average values. Here they are, different examples, different applications, how to find average velocity with the given velocity. Then you just integrate from whatever we ask you from 2 to 4, and then divide by the length of the interval. 4 minus 2, that's 2. And that was the last topic, unless you're in your class you guys cover more. Sometimes we cover U substitution in calculus 1 class, but sometimes it goes to the second calculus class. And second calculus class is keep going with integration, and we're gonna teach you more interesting ideas of integration, how they need to be done, more complicated integrals, and so on. You have to be very, very good with integration to make sure you do well in Calculus 2 class at the beginning. The middle part of the Calculus 2 class is amazing, about series and sequences, and at the end we do some applications there, volumes and rotations and so on, but at the end we even do polar equations. Finally, I want to point out that we actually covered some of the most important findings in the world. So there's a popular topic about top 10, top 17, top 20 equations that changed the world. And you will be surprised, but we covered something in Calculus 1 class. Yes, of course, Pythagorean Theorem is definitely a big deal. And it was created a long time ago. But we taught you in Calculus 1 class logarithms and properties of logarithms. I told you this is very important. It was created in 1610, and these properties are amazingly used in computer science, even though there were no computers at that point. But when computers show up, It's just really amazing that logarithmic functions saved so much space in the memory of the computer, speed up so many processes, because logarithm slows down the fast functions, and so it saves a lot of time and space in the computer memory. What do they mean by calculus? What is this? What do you recognize? This limit as the denominator goes to 0, blah blah blah. Yes, that's the definition of the derivative. That's definitely changed the world the way we know it by Newton, 1668. Then law of gravity, the square root of -1. That's the one we teach you in complex analysis when you take it. Then more formulas. Normal distribution will be given a bit later, probably in statistics class. Wave equation will show up in Calculus 3 class briefly, and then in differential equations. Remember I told you differential equations is the equation that has derivatives? Well, those are second derivatives, and those are partial second derivatives. We're gonna teach you what this curly derivative notation means. Curly means partial derivative. That's in Calculus 3 class. Fourier transform changed the world definitely by a lot. You're gonna learn a little bit later, but Fourier series are closely connected to the Taylor series, and we teach these in Calculus 2 class. So that's for you to know it's coming. Of course, some equations are going to be part of the differential equation class or partial differential equation class, and so those are important. Maxwell equations, second law of thermodynamics, relativity, E equals mc squared, of course. More equations will come from the partial differential equation class. Chaos theory, black holes, equations, those are the modern stuff. Look at the dates, 1990, 1975. So for you to know, Calculus 1 class covers something that literally changed the world the way we know it, and changed the science the way we know it. And that's amazing, and you definitely should be proud that now you're good at this, and now you're becoming a part of the scientific society with this bag of knowledge. Congratulations, and hope you enjoyed the video. See you next time.